Hello everyone, my name is Dewi from Chaoyang University of Technology, Taiwan. Today, I want to present my research paper titled Taiwan Stop Sign Recognition with Customized Anchor. This is the outline of my research paper. First, introduction, related works, methodology, experiment results and discussion, conclusion and future works. Traffic sign detection and traffic sign recognition plays an important domain in advanced driver assistance system. The arrival of modern breakthrough in deep learning has resulted in significant state-of-the-art results for traffic sign recognition, with much of the research focused on designing deep convolutional neural networks to improve the accuracy. However, due to the country-specific nature of traffic signs in color, shapes, and characters, it is difficult to find one such process to generalize a successful detection. For the purpose of this paper, we will focus on Taiwan stop sign detection and recognition. As we can see on the figure 1, this is the example of Taiwan stop sign and original stop sign. Our motivation comes from the lack of such a database or research system for Taiwan traffic sign recognition. One of the complicated concepts to understand when learning about convolutional neural networks for object detection and recognition is the idea of anchor box. In fact, if anchor boxes are not tuned correctly, our neural network will never even know that certain small, large, or irregular objects exist. Furthermore, we will never have a chance to detect objects without anchor box. The main contribution of this work can be summarized as follows. First, in this work, we will analyze importance of anchor calculation using K-means and original YOLO tree for Taiwan stop sign detection and recognition. Second, an analysis performance of YOLO tree with different anchor for Taiwan stop sign detection and recognition. YOLO V3 algorithms consist of fully CNN and an algorithm for post-processing outputs from neural networks. It divides the input image into grid cells of same size and predicts bounding box and probabilities for each grid cell. The backbone of the improved YOLO V3 is darknet 53, is making up of 53 convolutional layers to capture deep features, and it has been proved to be more effective than darknet 19, ResNet 101, or ResNet 152. By combining the anchor box and multi-scale prediction idea, YOLO V3 first assigns several anchor boxes to each scale features map according to the length and width of the anchor box. In figure 2, describe the darknet 53 structure. YOLO V3 has 3 anchors, which results in prediction of 3 bounding box per cell. Anchors are short of bounding box priors that were calculated on the COCO dataset using K-means clustering. Usually, it used to predict the width and height of the box as offset from cluster centroid. The center coordinates of the box relative to the location of filter application are predicted using a sigmoid function. YOLO V3 used K-means clustering to determine bounding box priors. It is sort of choose 9 clusters and 3 scales arbitrarily and then divide up the cluster evenly across the scale. On the COCO dataset, the 9 clusters we can see in this PowerPoint. Figure 3 shows bounding box with dimension prior and location prediction. Here, Px, Py, Pw, Ph are the x and y center coordinates, width and height of our prediction. Tx, Ty, Tw, Th is what the network outputs, and Cx and Cy are the top left coordinates of the grid. Pw and Ph are anchor dimension for the box. In the figure 4, it shows YOLO V3 architecture that used in this work. It used multi-scale fusion to make prediction. Using upsampling and fusion in FPN, the input image size of 416 times 416 is combined with 3 scales. The size of the 3 scales obtained is 13 times 13, 26 times 26, and 52 times 52 respectively. Detection on multiple scale feature maps improved the detection of small objects. YOLO predicts multiple bounding box per grid cells. To compute the loss for the true positive, in this research, we select the one with the highest IOU with the ground truth. This method conducts to specialization among the bounding box prediction ratio. Table 1 explains about the experiment setting in this work. Experiment 1 using the basic configuration of YOLO V3 with COCO dataset. In this dataset, it can detect 80 classes and one of them is stop sign. It used 255 filters and anchor calculated by k-means with 9 clusters provided. For experiment 2, we modify the class become 2 class based on our purpose work to detect Taiwan stop sign. We change the filter 2 plus 5 times 3 become 21 and use the same original anchor by YOLO V3. For experiment 3, we recalculate anchor by k-means based on our dataset. We use 9 clusters and produce new anchor. Furthermore, we use this experiment setting for training and detecting process. Since there is no pre-existing dataset for Taiwan stop sign, we had to custom a database and collect the image by ourselves. We used 400 images for each class. In this work, we only focus on stop sign. In the training process, we applied pre-processing steps. We manually detected and recognized the traffic sign. We used a bounding box labeling tools to give a coordinate location to the object we wanted to detect. The training model environment is a NVIDIA RTX 2080 Ti GPU, accelerator, 11 GB memory, i7 central processing unit, and 16 GB DDR2 memory. In the figure 5 shows the examples of the system detection results for the experiment 1, experiment 2, and experiment 3. We use 10 stop sign images for testing with various size and condition. The results experiments using stop signs image with the accuracy and time measurements could be seen on table 2. We can see in the image stop 2 GPG reached the highest accuracy on experiment 3. It gets 99.98% and 98.18% accuracy to detect 2 signs, and it needs 0.49 seconds to detect the stop sign. Compared with the experiment 1, using the same image only gets 84.40% and 94.20% accuracy, and it needs 0.51 seconds for detecting the 2 signs. In the table 2, describe the result experiments using stop sign image with different settings in the experiment 1, 2, and 3. Experiment 3 obtained the highest average accuracy and the fastest time detection. Table 3 describes the result of experiment 2 and experiment 3 using randomized 10 Taiwan stop sign images with different size and condition. From the result in the table 3, we can conclude that the result in the experiment 3 outperformed the other experiments. As we can see in the table 3, experiment 3 obtained the highest accuracy 97%, and for the time detection, it gets 0.50 seconds. The preview result of this experiment show in figure 6. The accuracy of image sign TW4GPT increased from 95.9% in experiment 2 become 97.01% in experiment 3. Further, the time to detect the sign in experiment 3 is faster than in experiment 2. Based on the experiment result on Table 2, Table 3, Figure 5, and Figure 6, we can conclude that the trend of accuracy increases and the time is decreased from Experiment 1, Experiment 2, and Experiment 3. Experiment 1 only can detect stop sign, but it cannot detect another sign. The best experiment setting is Experiment 3 because it can improve the performance accuracy and the time needed is faster than others. In the Experiment 3 can detect the sign precisely compared to other experiments. Anchor recalculation based on our dataset is very important and it is proven in our experiment. We need to define our anchor correctly so our neural network will know that certain small, large, or irregular object exist according to our dataset. In the future works, we aim to build the complete Taiwan traffic sign dataset with more images. We are still working on some modification to the current YOLO V3 and will combine with generative adversarial network GAN to detect similar signs. We intend to train a model with picture of higher dimension to increase the performance of the detection and recognition of traffic sign. Thank you.